Okay, yeah, it's our pleasure to have like Junyi here to like share about his work to us. And recently he just like put out an impressive work of trying to propose fault tolerant quantum machine learning algorithms, or not really machine learning algorithm, but okay, it's quantum machine learning algorithm because it uses like HHL to basically help us to speed up the training of stochastic gradient descent, and then like he benchmarked in very impressive large scale kind of like examples of like from the paper is like 103 millions parameters. And like Junyu will tell us more about like this work, and Junyu, the floor is yours.
Yeah, thank you. Yeah, so actually, my talk was previously I was planning to like purely give this presentation about the patient paper that you mentioned, but later I would feel that it might be like more fruitful to add another component, another part of my talk, which is about the NISQ algorithm. So I also add that part in. So this is so I make the title of the talk to be so-called quantum artificial intelligence from near term to fault tolerance. So
Okay.
it will contain both perspective NISQ and also fault tolerant algorithms. So this is my brief introduction of myself. I was currently a postdoc in University of Chicago, primarily, and also founded by IBM. So starting from 2021 now, and I have a PhD before at Caltech. So so those are like the affiliations that is funding my research, and specifically I want to mention there are two startups. One so-called qBraid, which is a quantum software startup, and also SeQure, so which is a startup for artificial intelligence and security. So so maybe I can start. So here are the papers that is the foundation of that's it, the foundation of this talk. So my talk was primarily based on those papers, and then primarily I will talk about like 2 layers of work. And firstly, the so-called analytic theory for the dynamics of wide quantum neural network. That is about so NISQ algorithm, and also towards provably efficient quantum algorithms for large-scale machine learning models. They are about like algorithms based on HHL. So those are like primary work I will mention in this talk. So this is my interest landscape, and which is about a combination of quantum physics together with artificial intelligence. And primarily, I will use quantum physics method and quantum computing method to understand better and study artificial intelligence and machine learning methods, and also see how physics principles will inspire like new algorithms and may be helpful, maybe might be helpful for those machine learning tasks. And some of them are quantum and some of them are classical. Those are like the landscape of the works that I have done and related to this spectrum. And then primarily I will mention those 2 layers of the work. For the NISQ perspective, I will talk about a theory, a so-called quantum neurotechnic kernel, so which is a theory for wide and large quantum neural networks, which get some provable methods that we could make predictions in theory. And also, I will talk about so-called HHL and plus quantum machine learning, and which is a used end-to-end example from HHL to try to solve the machine learning related problems, and a generic class of stochastic gradient descent actually. So those are the primary works that I will mention in this talk. So uh before that, so previously I thought that we are like for like a general audience. So, but but I guess the audience are like mostly for like quantum computing. I guess we can like try to skip those slides. And then if there is any questions, please like interrupt me in the middle. And then please go ahead and ask me questions. And those are like a very simple like outline of my talk. And firstly, I will give a very brief introduction of quantum machine learning. And then secondly, I will mention that the NISQ perspective, where we develop a series called quantum neural chain kernel to solve some dynamics of variational quantum algorithms. And then later, I will mention this large-scale HHL problem and give some final comments. So here is a brief introduction for quantum machine learning. So quantum machine learning is an area that is in very active development. So by definition, so it was using quantum computing method to run some machine learning related algorithms, and potentially it might be better than pure classical machine learning methods. So there are many like big picture problems. So firstly, what is quantum machine learning? So different people might have different definitions actually. So why quantum machine learning? Why we are going to use it instead of pure classical machine learning? Where is the potential advantage? And also, what is a typical problem for quantum machine learning? Do we have a killer applications? And what if there is a supervised learning task, then it should have a database. And if do we have a quantum database, or it has to stay classical? And finally, what is quantum machine learning algorithms? So those are like the generic big picture problems that we are going to understand. So all machine learning related works are trying to maybe understand part of the problem, and also our works are also trying to make efforts on those directions. And specifically, the reason that I bring part of the reason that I bring the NISQ and fault tolerance together is because of the noise. And we know that in the so-called NISQ area at the moment, quantum noise will limit the implementation of quantum circuits at a large scale. So there are lots of errors and noise in the devices that might be limiting the application of quantum computing. On the other hand, quantum error correction is very challenging, and those algorithms are challenging to build at the moment. So we might still have a few years from the current NISQ scenario to the so-called full fault-tolerant quantum computing in a lower scale. So the question that we have at the moment is that how the quantum noise affect quantum machine learning problems. So one example or one intuition is that, so we know that there are many like classical machine learning algorithms that are already like kind of robust against noise. So in a stochastic gradient descent, the reason stochastic is because we actually just need a few manually added noise and in order to enhance the performance of the algorithms. So and the question currently people have, or we have, is that how much quantum noise and then actually could affect quantum machine learning problems or quantum machine learning algorithms. Are they like positive or a negative? So the development of quantum machine learning algorithm has to be like associated with those noises, development of the hardware and also the noise. So, okay, so those are some generic comments or introductions. And again, so if there is any questions, please interrupt me in the middle, and then please feel free to ask me questions. And then I will start to talk about the NISQ algorithm I will mention, and a theory for a generic class of NISQ algorithms, so-called quantum neural technique kernel, QNTK. So, okay, let's start. So we know that, so in the NISQ era, so the primary quantum machine learning algorithm, or the primary algorithm in general, is so-called variational quantum algorithm, VQA. So the definition, I think many of you are already very familiar with, is very simple, that you just have a series of maybe local gates and rotation angles, and then maybe rotation X, Y, and Z, and then together with some like a fixed gates, like a C naught or some other gates that provide entanglement. And this is an example of such circuit. And note that those rotation angles are parameterized by classical variable theta. So and then in the total, and you are able to like make a unitary, and then you could use this unitary to do things. And for instance, you can act it on a state and then try to measure some operators. And you can use this operator itself, operator measurement result as a loss function. And after you have this, and you are able to like use some classical machine learning or classical optimization technique to optimize the corresponding loss function to get some optimal value of variational angle theta. So that is the logic of all those variational quantum algorithms, including QLA and the quantum neural networks. And a typical simplest example is variational quantum eigensolver and NISQ quantum computational chemistry. So which is that you are basically trying to minimize the expectation value of an operators. So let's say the Hamiltonian of your system, you want to find its ground state, and then you are going to make a so-called variational quantum ansatz, and looking at like this and trying to compute the corresponding expectation value, and then in order to find some approximate value of the ground state energy. So that is the logic of those kind of so-called variational quantum algorithms. So however, so although people try to make progress in practice, like trying to use this algorithm to solve some problems, for instance, in chemistry, in optimization problems, and they get some partial success and in practice. However, so there are also still a lot of like troubles on theoretically understanding how those kind of algorithms could perform. So simplest question is that why this kind of method will work, or why it when it's a situation that we cannot work. And a famous so-called no-go theorem indicates that why it cannot work is so-called the barren plateau problem actually shows some negative result on this kind of variational quantum algorithms. So my theory actually have another insight or perspective about this called barren plateau problem here, but I will mention this later. So that just indicates that we still need some theoretical understanding on how this variational quantum algorithm work, and how good this performance will be in theory. And there are still lots of mysterious phenomena that we have to understand better. So some general question about variational quantum algorithms I want to understand, or I want to solve is firstly how to choose variational ansatz. And if I have like two different variational ansatz, and then which one is better, can I determine this actually before you do any training? So for instance, you switch the rotation Ry to Rz, and is there making any effect on your performance of training? And that is the question. And also, second, how good the convergence will be, at least in some limit. And if I use some classical methods to optimize it, for instance, stochastic gradient descent, and how good the conversions will be, and how is the dynamics of stochastic gradient descent look like. And finally, I want to understand is that is there any difference between quantum machine learning and classical machine learning? So that from my introduction, you can see that this variational quantum algorithm is a spatial way to construct the loss function in a classical machine learning problem. And then why this kind of method work and why it's potentially better than classical counterparts. So that is also the primary task that we want to understand. So my theory was trying to make partial progress on trying to understand all those related problems. So the theory could be roughly illustrated as the following. So according to my discussion, so just now you already know the generic form of the variational ansatz, which is given by a bunch of W and X, where W are fixed states and X are like maybe rotations parameterized by variational angle theta. And then you use it to act it on the known state, and then compute a loss function for a given variational angle theta. So here we are interested in choosing a spatial but generic loss function, which is so-called mean square loss. So here we are interested in the expectation value of this variational state on the operator O and minus O0, which is a number. So you can set O0 to be an arbitrary number at the moment. So the reason I keep O0 is because I want to unify this with supervised learning. You can see that this this optimization task itself was a spatial case of a supervised learning, which only has like a single data. And in the VQE, variational quantum eigensolver type problems, you can keep O0 to be actually 0 for simplicity. Say your task is to minimize your Hamiltonian and O. And then specifically, I want to define so the difference between the neural network prediction and this O expectation value minus O0 to be epsilon, where this epsilon is so-called residual error or residual training error. So in the language of a linear regression. So this thing I will call it epsilon, and then so the loss function is half of epsilon squared. So this is a standard mean square loss. And then so the gradient descent algorithm in the simplest form is given by this famous formula, where this fancy D was the difference between the time steps, two time steps, time t plus 1 minus time t for the variational angle theta. And then so this was equal to minus eta times the partial derivative of the loss function over the variational angle, where eta is so-called learning rate, so which is a positive number. So usually it's setting to be very small, a small positive number. So this is a famous formula for gradient descent, and I'm sure that everyone familiar with machine learning will know it. So this is also appears in the calculus book. And then the point of this so-called neural changing kernel theory or quantum neural changing kernel theory is that so we are not only interested in the updates of the variational angle. So instead, we are also interested in the updates or to time difference of this loss function or the residual training error epsilon. And if we compute the updates of the variational angle of the residual training error epsilon, and assuming that the updates of the variational angle is small, using the Taylor expansion, it will be given by the derivative of the residual training error over the variational angle times the updates of the variational angle itself. And then after you have that formula, at least in the first order approximation in the Taylor expansion, and then using a little more algebra and taking the derivative, you can show that the updates of the residual training error is equal to minus the learning rate eta times a quantity so-called k, which is the quantum neural changing kernel times epsilon itself. K neural changing kernel is given by the square of the residual training error over derivative over the variational angle and the summing over all the variational angles. So this is a non-negative number, which we currently call it quantum neural changing kernel. So you will immediately see the following fact. So you know that the time updates were in the infinitesimal limit. The derivative of your residual training error is equal to minus a constant, minus a number times the residual training error epsilon itself. Specifically, if this k is a constant, then you will immediately notice that. So you will have a solution on this recurrence relation, or in the infinitesimal limit, it becomes a differential equation. And then a derivative of a variable is equal to minus the constant times the variable itself. And the solution of this simple differential equation is going to be exponentially decay. So exponential decay solution. And in the finite step limit, and then the difference equation version, you also will have the closed form solution. If the k is a constant, and then it's given by 1 minus eta k to the t, where t is the number of iterations, and then it's purely a exponentially decaying solution, where this k is basically determine how much that you will have for this exponent in this exponential decay. So okay, so if k is a constant, then we'll have a guaranteed convergence, and then we know an exponential decay relation, and then we exactly solve the gradient descent dynamics. It's good. However, in general, k is highly fluctuating in the variational angles. So you can derive a formula. So for instance, in this case, for the variational quantum circuits, and then you can see that they are like highly depending on variational angle theta in general, and it might be very complicated. So that is a feature of so-called representation learning, which means in the machine learning language, which is that if the kernel itself is changing, so in terms of in the terminology of the kernel method in machine learning, that means that the feature map itself is changing. So actually, this k can be understood as the same as the kernel method kernel. And then this is basically an effective kernel during the gradient descent. And then because your kernel is changing, then effectively your effective feature map is changing. And that means that you are extracting features from your training data in the machine learning language. But it's just a word that I will explain later. But the point is that in general, k might be like fluctuating. So then you cannot get this closed form solution. However, so the theory is also trying to address when in the case where this k is approximately a constant, if you get approximately a constant k, then you also get partial success because then you can use this formula and its perturbation as an approximation. So this is a point of this theory, how quantum neurotechnical kernel theory works. So a simple example is in so-called lazy training. So which means that if your variational angle is almost fixed, it's perturbing around a fixed variational angle, a fixed value. In this case, that means the training is lazy and you almost does not move. And in those cases, of course, your kernel has to be a constant because it's a function of theta. If theta does not change, then your kernel is approximately a constant. And then using that way, and you can also do perturbation theory, you will assume that, okay, so if the variational angle theta is perturbing around a fixed value, and then you can get predictable dynamics. And you can do this perturbation theory order by expanding in terms of small variable eta. And then, so here is the example of the solution of the first order. So this epsilon f is a free theory solution, so which is the leading order solution, and in terms of perturbation theory language. And then epsilon I is perturbation, so which is instead of exponential decay, it was a polynomial t, and which is a linear function times the exponential decay, which overall is also dominated by exponential decay in a long time, so it will also vanish. So that is the first order perturbation theory. So and then you can do this calculation order by order, and then there are like ways to do this calculations order by order, and then you can also get predictable dynamics. So until now, so my explanation was mostly about generic machine learning, including classical and quantum. It's the same or almost the same conclusion. So what's the spatial for quantum here? So here I will show you something more quantum or quantum related. So which is taking the limit of so-called deep random quantum neural network. So the idea is the following: as long as we derive the formula k, and for the quantum neural technique kernel in terms of variational ansatz, we can make some assumptions. A typical assumption that we make is that we will assume that your variational ansatz u is sufficiently random. Say that they are like randomly sampled from the unitary group. If it is randomly sampled in the unitary group, and then you can do an integral of this on all samples of this u in terms of ensemble, and then try to get closed form formula of K. So this method is so-called K-design assumptions, and which is widely used in, for instance, cryptography and even related to quantum properties of black holes. So, but basically it was just an integral that you are making an integral over all the possible realization of your variational answers. And then the so-called K-design K just means that your prediction is accurate up to case moment comparing to fully uniform distribution on the unitary group. So for instance, in this language, a Pauli ensemble, a Pauli group is one design and a Clifford group is two design. And for instance, and then after you make this integral, you can get some simple but beautiful formula for this neural chain kernel. So you can show that your there is the average of your neural chain kernel, which is proportional to L, where L is the number of training parameters. And then it's if you have more training parameters, your neural chain kernel gets larger. And in fact, it has a closed form formula where L times trace O squared divided by N squared, where N is the dimension of Hilbert space, and O is the operator that you are trying to optimize or you are trying to learn. And L is the number of training parameters. And it's a very simple formula. And then you can also, because it's a distribution, you can also compute a standard deviation instead of the average. And the standard deviation you can show is actually proportional to square root of L divided by N squared. Where square root, this scaling is important because if you compute delta K divided by K bar, which is a relative standard deviation, so that will show in the scaling of 1 over square root L. So that means that if you have the L, the number of training parameters, to be much, much larger than 1, and then you will get the so-called frozen limit, where delta K divided K bar is much, much smaller than 1. So which tells you that if I randomly sampled from a unitary and a unitary distribution from a unitary group, and then you get almost a fixed K, where K is given by L times trace O squared divided by N squared. So it will not opt by this value and a lot. So it will be around this value. So that means that indeed K bar can be like approximately a constant. So this is the assumption of so-called deep quantum neural network. However, so this assumption also kind of make it theoretical because you could notice that this is divided by the dimensional Hilbert space n. So you can say that so because for instance, if you take O to be Pauli operator and trace O squared is n, and then n divided by n squared is 1 over n, and then basically your neural net kernel K will scale as L divided by n. So that means that if you cannot make your number of training parameters to be comparable to the Hilbert space dimension, then you will get a very small neural chain kernel. So that is a bad sign because that means that your convergence is slow. So that will make this model to be more a toy model. And this is also an alternative interpretation or understanding of so-called barren plateau problem that people historically discuss. So, however, on the other hand, this theory can also make practical usage. Because, for instance, even if this kernel itself is not frozen, so it is also an approximate way to, it's still an approximate way of trying to determine how fast your gradient descent dynamics have. And for instance, if you have two variational answers and you don't want to do training for both of them, you only have one piece of money and to run those variational quantum algorithms. And then what you could do is to compute the neural net kernel actually before you do any training. And you can choose a larger one, and which shows that you will have a higher gradient or higher faster dynamics. And in the case of higher neural net kernel values. And then that is a way that you could select your rational answers and you make your performance better. Using this formula, you can also estimate how much time you will take and for a given residual training error precision and how much time or how much iterations you need for performing the gradient descent dynamics. And then using that way, you can try to design your hardware and or setting your hardware parameters in order to perform those experiments. So just now what I'm talking about is optimization problem. And then now I will upgrade this problem from number to matrix. So which is the idea is the following. So which is that you can embed. So for the supervised learning test, you will have a data x delta, and then you can map this delta x delta to a feature map in quantum feature map by mapping it into a quantum state, which is given by phi of x delta. And then as long as you know this feature map, you can also do the measure some operator OI and a bunch of different operators. And then in this case, you will make the residual training error a vector. And also you can do the same calculation as I have done before, but all the algebra becomes matrix algebra. So, and the kernel now is really a kernel, which is a non-negative and a semi-definite matrix, positive semi-definite and also symmetric matrix instead of a non-negative number. So, and this matrix itself is with a size with the same as the dimension of your training data and the size of the training set. And if you have a training data in your training set, and then this matrix will have the size a times a. So that is the kernel that you have. So that's why it's called this quantum neurotraining kernel. So because it's a really kind of a kernel, you can show that it's the same or the same interpretation of the kernel in terms of kernel method in classical machine learning problems. So, and you can also have the same phenomena and the similar frozen property of so-called frozen Q and TK. And it will also have the so-called exponential convergence, but it's in terms of matrix algebra. It's a matrix multiplication and matrix exponential. And you can also do the perturbation theory as I introduced before, but the algebra might be complicated and because it has lots of indices. And often in those cases, you have to visit so-called quantum meta kernel, where the meta kernel was actually a higher derivative instead of the first derivative and of the residual training error over the rational angle. So you have to visit the second order derivative in order to do the perturbation theory. So, but I will not talk about those discussions in this talk, but I will address those issues. Maybe I already addressed those issues in my paper, and you can take a look if you're interested. So until now, so they are all analytic results, but we will also have a simple simulation or experiment. So the first experiment that we have was like a simulation in the real IBM environment, where we have like 3 qubits and they're doing a classification problem in 2 years ago. So it's very simple, but you can also do that experiment easily nowadays with a larger amount of qubits. And then what we are going to show is that you might have a fixed value of the neurotiny kernel eigenvalues, and even in the noisy case and in the late time, because I already described that's a point of native training as long as your rational angle does not update that much. And in those cases, and your kernel will be frozen and or fixed as a constant. And then those picture basically shows that basically your kernel eigenvalues are almost a constant and cannot change that much. Only change a little bit at the late time of training if your rational angle theta is almost a constant. And here there are some like verification of scaling that I have showed in the theoretical calculation. That the key point of the theory is that your standard deviation k is proportional to the training parameters L, and the relative standard deviation delta k divided by k bar is proportional to 1/√L. So which are the typical scaling we have on so-called deep and wide quantum neural networks. And then so in that case, because your neural tangent kernel is almost constant, so you will get a perfect frozen dynamics, where here is a numerical example in the noiseless simulation, where you can show that, your residual training error is exponentially decaying almost perfectly, and then you will have a frozen quantum neural tangent kernel during your training. So okay, so those are like the primary part of the SNISC discussion. But aside from that, I will also mention one of my another work, so which shows that the effect of the noise for the variational quantum algorithms. So in another set of works that we have, we show that so there are some noises and in the variational quantum algorithms, and we know that in classical machine learning, noises might be helpful. One of the reasons is because in the stochastic gradient descent, it will help us avoid the saddle point. So we know that machine learning algorithms using gradient descent, it can not only converge to a local minima, it can also converge to a saddle point. So the saddle point, at a saddle point, it might be stuck forever if you don't add noise. However, if you add noise, and then it can perturb around, you add some thermodynamics around the variational process, and then it will get away from the saddle point and then go to the local minima and potentially go to a lower saddle point and also potentially a local minima. So that is the point that in our paper that actually we replace this noise to be the quantum noise. We actually do an example where in this picture that we have like a 6 or 7 qubits, I forget, for the real experiment in IBM. So we actually find for the same set of algorithms, and the noisy case is actually outperforming the noiseless case. So that is a toy example that why this kind of a method work. And we also have underlying theory to try to address this problem and say how the noise can help classical machine learning, and underlying a set of recent breakthrough in the theory of non-convex optimization. And this work indicates that, of course, so we have to do quantum error correction for tolerance quantum computation. But in order to approach that, we have to mitigate to reduce the effect of a lot of noise. And then the theory that tells you that in certain quantum machine learning applications, you don't need to kill all the noise. As long as your noise was like under some threshold, and it might already be not hard and even helpful for certain quantum machine learning applications. So in this case, you don't need to use photonic quantum algorithm to kill all the noise, because killing so much noise are so hard for the current technology. So that's why that we are proposing that this kind of method might be a good idea for variational quantum algorithms. So okay, so until now, is there any questions?
There's no from the audience, but I have a quick questions like regarding of the deep neural network assumption for your QNTK. So for this one, recently, I think the group from Los Alamos, Marco Cerezo, kind of shown that like for deep neural network, it kind of converges, like the output statistics of given observables basically converges to like Gaussian processes. And do you know kind of like any link between this and that? Because I know for classical deep neural network, like essentially it's like Gaussian processes and NTK, like neural tangent kernels would be kind of related. Do you see some links over there?
Yeah, so actually we are the group that shows earlier to Los Angeles people that in for deep and wide neural network and in quantum neural network, it will be a Gaussian process. So it's connected. Firstly, the prediction of your residual training error is Gaussian. And secondly, you will have a fixed neural network kernel at the early time of training. And thirdly, your dynamics will almost do not change the value of the neural network kernel for wide quantum neural network. So those three things are closely related, and according to our paper. So our artist paper actually already shows that this is a correlation, and if you're averaging over those ensembles, the correlation will be Gaussian. In the case of wide, sufficiently wide, very in quantum language, it's going to be a very deep random quantum neural network. So those are closely related. And then later, and I think Los Angeles people give more like a clarification and also discussion along this those directions. But I would regard those as parallel efforts, and then along those direction. But usually their paper will not use the terminology quantum neural network kernel, and the quantum neural network kernel is mostly, or neural network kernel was mostly used and defined in our paper.
Okay, yeah, for sure. Thanks.
Okay, thank you. And then in the chat, so there is also a question. What do you mean by wide quantum neural network? Great. So actually, so this is a great question. So so in our paper, we say the definition of the wide quantum neural network by the following. So firstly, wide neural network, quantum neural network means that you will have a large amount of training parameters. Your L has to be large. At the same time, you also have to have enough dimensional Hilbert space. So your N has also to be large. So the precise definition is that both L and N has to be large is a large is a wide limit in our paper. So the reason we require both L and N to be large has some technical reasons. And this delta K divided by K bar is only one like criterion. And also this formula we recently showed that after some refined after we look at some refined structure of this ensemble of assumption of random unitary, so then you have to make this to be both work in terms of N to be large and also L to be large. So this formula, simple formula, is just a sketch of our like phenomena. And also, so that is the definition. But so this is also used in classical machine learning language. So in classical language, so width is like for a single layer of your neural network, width is the number of neurons, and the depth is the number of layers in your neural network. For instance, in the simplest MLP model. So the large width neural network is just means that your neural network is very wide in each layer. So that is a classical language. But in quantum language, it is in some sense, for quantum neural network, in some sense, it is a single layer classical neural network. So then the quantum depth becomes a classical width. So here in our paper, we are using the classical language, which means that it's a wide quantum neural network, which means that you have a large L and also large N. But in quantum language, that also means that your quantum neural network is very deep. So that's the answer to the question.
So essentially, you are saying the way we define the structure of quantum neural network is slightly different from how we define a classical machine learning context. So you have a different set of terminology. Is that correct?
Yeah, because quantum neural network does not have an activation function. It does not have a nonlinear activation function. It's basically another sort of architecture. So there like a appealing or nonlinear effect are hidden in the feature maps, and also in the like entanglement like between different qubits, and after you applying like different C0 gates. So it is basically a different architecture, but if you want to view quantum neural network as a spatial classical neural network without the activation function, because there is no activation function, then it has to be a single layer. So in that case, the quantum terminology depth becomes a classical width. So that is just a traditional language. And there's another question: why K is this product not writing it in a square? So it's not a silly question; it's a great question. So the reason that you can write it as a square in this case. The reason that I don't write it in a square is that in general case, your each z or each epsilon will have indices. And then in that case, your K becomes a matrix. So in that case, you cannot write it into a square anymore if you carry indices. In this spatial case, you don't have indices. You only have one indices because you only have one dimension data. So that's why I write it in this way. But in this one dimensional case, I can, of course, writing this to be like a square. So, but in general, the kernel itself is a matrix, and then so you have to keep indices, and carry indices, you cannot write it in terms of square. Okay, great. Thank you for the questions. And then we have a limited amount of time, so I need to like move to another topic, another also interesting and fascinating topic about how to apply HHL into machine learning methods. HHL, I think many of you are already very familiar with. This is a famous photonomous algorithm that could solve your large-scale matrix inversion problem for sparse matrix. And it's an exponential improvement in known classical counterparts. So basically, the task is sparse matrix inversion. You have AX equals to B. You want to compute X equals to A inverse of B. So this is one of the principal paradigm for photon quantum computing methods. So, or principal paradigm for like a photon quantum computing quantum machine learning algorithms. So many people claim that they can do quantum machine learning with known quantum speed up, and they might use a layer of HHL inside. And our goal is to try to use it in some useful classical machine learning tasks. So before we look at machine learning, we can looking at some other related directions. So which is solving ODEs. So here, what we are interested in a historically very important work by Andrew Charles and his friend, and the first author is Jim Panil, who is also my collaborator. So the idea of that paper, like 2 or 3 years ago, is the following. So people know that this ODEs, nonlinear ODEs, could be linearized to a linear ODEs. So this technology is called Kalman linearization, which will bring a set of systems of ODE, nonlinear ODE, to infinite dimensional linear ODE systems. And then you can like try to solve those linear ODEs and instead of the original nonlinear ones. So we know that linear ODE can be solved by HHL algorithm, so which has this exponential quantum speedups for known algorithms. So so this technique is realized by so-called Kalman linearization. But this Kalman linearization bringing your like a nonlinear system to an infinite set of linear systems. So because it's an infinite set, so you have to do truncation. And people find that if your system actually has a dissipation, and which means that those ODEs are nonlinear dissipative ODEs, in those cases, you are able to like control the error in the truncation of Kalman linearization. So then that means that dissipative systems could be efficiently linearized. And then after you linearize it, you can use the HHL, which will have an exponential capability. So this combination leads to an exponentially efficient algorithm for solving ODEs, other than like classical counterparts, and it seems that it's gonna be exponentially efficient. So that's a historically very important work, shows that nonlinear ODEs can also be solved by quantum computers efficiently. And then we will use this as a basic pipeline into the machine learning. So we know that dissipation is an important factor into this potential quantum speedups. So we also know that machine learning tasks, many of them is actually dissipative. For instance, famously, we know that the so-called diffusion model in generative arts, and right, so they are like a dissipative process. And in general, it's also true. And firstly, a simple argument is that gradient descent process itself is a dissipative process. So if we treat the gradient descent as dynamics, so they are like a open first order system that cannot be described by Lagrange dynamics, which you can very easy to prove. They has to be an open system. They cannot be a closed system. There are some other reasons that to support that actually our brain or machine learning task is actually a dissipative system. So I list a few reasons from biology to feature information and activation functions, but you can check about those things later. So actually, what we find is some combination of those facts will lead to a potentially efficient algorithm for solving stochastic gradient descent. So firstly, the technique towards the ordinary differential equation could be used to ordinary difference equations. And we know that the stochastic gradient descent process itself is basically a set of nonlinear coupled ODEs. So they are like basically no difference aside from the finite difference instead of infinitesimal difference. The same metrology will work. And then the next task is that we should try to figure out where this algorithm actually should work and how this could work in the machine learning process. In the actual machine learning process, what we find is that the Hessian eigenvalue, so which is the second order derivative of your loss function, which is a matrix, and you diagonalize it, it becomes an eigenvalue, and then eigenvalue will characterize the stress of the dissipation. If your Hessian eigenvalue have positive eigenvalues, so that means that you are in the phase of dissipation. If you have negative eigenvalues, then it's something non-dissipative, which is amplification and divergent. We call it divergent modes in the paper. So in actual learning process, and actually what we find is that at the beginning of training, actually the number of dissipative modes is much more than the divergent modes, which means that your Hessian eigenvalues are highly asymmetric. Your positive eigenvalues are much more than negative eigenvalues. So in that case, so at the beginning of training, so then you are in a highly dissipated phase because you are actually learning things, and your neural network becomes very sensitive. In that case, and it seems that we indeed are able to use this ODE solver to solve a machine learning task. And then around the end of training, so there are comparable number of positive eigenvalues compared to negative eigenvalues. They are roughly the same amount. So that means that so you cannot really use this algorithm because your system is not dissipative anymore. So a special example is that around the local minima, if you already know that your system is around the local minima, Hessian spectrum are positive semi-definite based on the definition. I mean, the definition, the Hessian local minima just means that Hessian spectra are positive semi-definite. And then we indeed get the dissipation. And in that case, we will indeed have the guarantee. So then basically that finish the pipeline of the algorithm. At the early stage of our training, what we can do is that we will compile the neural network to a quantum computer, and then we use the ODE solver to solve it. And then we know that that process itself will have to be very fast, and also potentially like a exponential speed up and against known classical counterparts. And around the end of training, if we already know that the Hessian is going to be more symmetric and they are equal number of positive and negative eigenvalues, then we stop doing quantum and we download the states and the data and keep doing it classically. So that's a pipeline. So but they are also uploading, downloading problem. That is very important, that I will talk about later, which is a perfect arena to apply both quantum and classical machine learning important techniques. So this picture is a dream that I have. It's not really realized, but it's something that we are trying. So my dream is that because right now, classical machine learning has lots of training parameters, and they are very costly in terms of energy, and they might be like not very sustainable. Actually, I see a news yesterday that right now the machine learning computational cost was growing double exponentially with time. Double exponential means that it's 2 to the 2 to the t, where t is the time. That the demand grows very, very quickly. That we are using double exponentially more resource than we have in the past. So that is a huge cost. So if we are able to take a log on those costs by using quantum computers, that will significantly save using energy. And maybe that is potentially the future, that maybe in the future, people will like really use a quantum computer and run those large scale machine learning models. So that is a dream. But this has to be realized in a fault-tolerant quantum computing regime where we have so maybe some smart people will come up with NISQ algorithm or in the middle. But in this work that I'm showing is that maybe large scale HHL is possible to try to resolve that task. So and here, so basically there is a pipeline of our work. So an important ingredient of the story is that we have to figure out the input and output problem of HHL, which is very important. And luckily, there are actually some classical technology that allow us to try to figure it out. So this is called pruning. So which is the following. So actually, our current neural network is actually kind of like a brute force trained way that we take a large amount of data, very, very large amount. But actually those neural networks around the end of training, they are like very, very sparse. So if you take a look on like, for instance, like GPT-3 and those training parameters around the end of training, and these are usually like very sparse parameters. That means that many weight parameters are nearly zero or approximately zero. So that means that those parameters does not take that much effect. And in fact, they are like the structure of the neural network matters, but those parameters are like sparse itself. So this inspire a so-called a thing so-called the lottery ticket hypothesis. But that is something also in a huge amount of debate in the classical machine learning community, which says that for a given dense neural network, there also always exists a sparse version of the neural network that has a comparable generalization error comparing to that dense neural network. But the neural network itself can be like pruned to be sufficiently sparse. So that sparsity itself allows us to do the uploading and downloading problem. So for the uploading problem, for uploading the classical training parameters to the quantum devices, that might be easier if we have the so-called quantum random access memory. So which is currently still technology that is in the process of development, but we have to have that maybe in the future. But for the downloading problem, we know that for dense quantum states, if they are like full rank, then it's computationally hard to download the full quantum states to a classical computer because it has exponentially number of components. So in those cases, what we could do is that if they are like sparse, states, and then of course we can download it because most of the components are zero. So actually we design some tomographic methods that if you know the sparsity of the states, and then there are ways that scales polynomially allow you to do the tomography to download those quantum states to a classical computer. So the pipeline is the following. So if we have QRAM, we can directly upload a dense neural network. But if we don't have, we will have weight pruning to prune it to a sparse neural network with a comparable performance and load it into a classical ODE system and use the quantum computers to solve the ODE. And after that, we will do measurement and also pruning, and then it will give you an output sparse neural networks that will keep run classically in a non-dissipative regime. So actually, we do a simulation classically of a large-scale classical machine learning model for a huge number of training parameters, from 7 million to 100 million training parameters. And what we find is that indeed, so the point of that simulation is to say in which regime the learning process is actually dissipative. And what we find is that at the early stage of training, actually, it's indeed that the Hessian spectrum is asymmetric. And looking at those figures, and the y-axis is a time step, and the x-axis is a eigenvalue, Hessian eigenvalue spectrum. At the early time, so what we find is that at the early time, it has like a more positive eigenvalues, much more than negative eigenvalues. And then, so that means that at the early time, and you probably can do this quantum ODE solver. But after a few iterations, after some maybe significant amount of iterations, and then your neural network stop learning and it becomes a fine tuning stage. And so in those cases, and then your Hessian eigenvalue are more symmetric than before, which means that you will have maybe a more negative eigenvalues comparing to positive eigenvalues. So in those cases, so we are able to stop the training and doing tomography and doing pruning, and such that we will have downloaded into the classical devices and keep run the rest of the iteration. So this program contains lots of science inside, including large language models, if you are doing like large scale benchmarking, and also quantum linear system equations, quantum Kalman linearization, and also sparse training, lottery ticket hypothesis, shadow tomography, and also QRAM quantum memories. And one of the theory behind this like dissipation, non-dissipation is related to so-called information bottleneck theory. So, okay, so that is a brief introduction of this part of the work. And then I will give a very simple final comments, and then I'm free to questions. The final comments is that quantum machine learning is a very promising area, and potentially quantum device might be helpful for large-scale classical machine learning problems. In the near term, variational circuits are primary algorithms running in the NISQ devices with noise. Circle tools like a quantum neural tiny kernel are very useful to design those devices using first principle. On the other hand, machine learning algorithms are sometimes robust against the noise themselves. In the NISQ devices, noises might even help us to avoid the setup points and improve performance. So in the long term, HHL is one of the main ingredients for quantum machine learning algorithms. In our work, we design an end-to-end HHL algorithm for sparse dissipative machine learning algorithm and show that they are efficient quantum algorithms, which might be universal, robust, generic, and provable. So their knowledge, also a generic lesson from those is that because I'm from more fundamental physics background, I find that the knowledge from fundamental theoretical physics is very helpful for quantum algorithm designs, where I use concepts like quantum chaos and random unitaries and dissipation. So they might be very useful for designing like machine learning applications, quantum machine learning problems. So those are like the final comments. So this is a sketch of some other works that I did, but probably I don't have time to like introduce them. So, but here is a small advertisement on my startup where we have SeQure, so which is powered by machine learning scientists and also like a cybersecurity scientist. So our idea is trying to combine so-called post-quantum cryptography together with artificial intelligence, and in order to find the intersection between cryptography and together with AI. So we have basically two products, and the first one is used for real-time fraud detection and on-chain monitoring, anomaly detection for blockchains. So the second application is so-called SeQure Robert, which is a cryptography enhanced large language models. So those are helpful for doing trading and also investment and also banking, and also it becomes an end-to-end encrypted. It's a cryptography enhanced large language model that could preserve the security of your alliances. And that is a small advertisement. And then thank you very much for your attendance. And then right now I'm very much free to questions.
Yeah, thanks, Junyu, for the very, very informative talks. Like basically, you kind of your line of work basically give a lot of the tool for us to exploit the potential of machine learning. So for the audience, if you have any question, feel free to unmute yourself and just ask the questions. And while the audience is thinking about the question, maybe I could just quickly ask one question. Could you go back to the figures, C, like the one that you have patients, the
Yes.
3 pictures over there?
Yes.
Yeah, I'm specifically want to ask about figure C on the left, right? So for that
Yes.
one, is so what why there is a kind of downward spike over there, and what's happening?
Okay, that's a great question. So actually, so the reason is that I put figure is corresponding to this pruning strategy. So in our calculation, we are using the brute force pruning. So which is basically that we are which is also called pruning from scratch, which is that we have, let's say that we have a dense quantum neural network. And then during the algorithm, we get a dense quantum neural network at the end. And then we imagine that those dense quantum neural network are encoded in a quantum computer, and then we need to do tomography. And then we are going to prune the components that has the lowest weights, and the absolute value of those weights are very small, relatively small, and then we throw them away. So that could be done by projective measurement. And then you just measure the state and say a bunch of 1 and 0, and using that pattern to determine so which are non-zero components, which are zero components. And then after you do one pruning, and usually the accuracy will decay because you are pruning from scratch, directly setting some of the weights to be 0. But it will not decay to empty, but it will still decay. What we find is that after a few iterations of this training, and actually this amount of decay is more and more slower, and later it becomes ignorable, and also much less decay, and it will be kept as almost the same amount of the accuracy without pruning. So that is the strategy we do. So this bump are basically based on this pruning. So which is that I'm setting sequence of your training parameters to be 0. So the reason is in order to solve this input-output problem of quantum classical communication, because quantum computers can only communicate with classical devices with a dense with a sparse state, especially downloading, because there are exponentially many training parameters. We cannot download all of them, so we have to do pruning. So that's why it has this kind of bump.
Right. And how many qubit? How big is quantum system size that you use to do this simulation?
So this simulation itself is completely classical. We are basically doing classical simulation, classical computation. We didn't do anything in quantum, and the goal of this was firstly to test this pruning method, which are useful which should be used in quantum devices, and also we the goal of this simulation for running this task is going to verify which regime in training the system is dissipative, such that it could possibly potentially admit such a quantum algorithm. But we didn't do a quantum simulation itself. We didn't encode it into the quantum computer because this really has to be very, very large scale HHL. So if you have a very small amount of simulation, and this number of parameters in this Kalman linearization grows very, very fast. So we are not able to do that until we will have a really fault-tolerant quantum computer, or at least the early stage fault-tolerant quantum computer. So we purely do a classical simulation in order to show this generic picture work.
Yeah, how many the logical qubit do you think is sufficient for your algorithms? Is 500 logical qubit sufficient? Because I remember like
it's probably around that number. It's probably around that number.
Okay, I see.
Basically, the number of logical qubits are like taking a log on these numbers. So if you take a log on those numbers, this estimation are like relatively low. I mean, I think that is because my basis is E. If you take a basis of 2, it's gonna grow to be like of all the hundreds logical qubit. And also you have to have like uploading and downloading machine. So maybe you need more.
Right. Okay, got it. So that is still not okay. Maybe I will just ask one last question because of the time. So like for A, right, as in you kind of like stop and restart it again, right? Like how do you kind of like gauge when to stop for the training in order to kind of reinitialize to get like a lot of like positive eigen value in your Hessians? You have to keep calculating the eigen spectrum of the Hessians when you kind of like to inform you when to stop.
Yeah, so great. So the reason we have to stop is because the system is not in the dissipative regime. So if it is not the dissipative regime, then we have to stop to instead of like introducing to try to introducing like less error. And then so maybe a good way is to keep computing the Hessian eigenvalues during a few iterations of training. However, that will be computationally hard. Not very easy to do to get this Hessian eigenvalues. So that can be done like by like classically a few benchmark or experiments. So which is that you can like try to like if you learn some experiments on where to stop, and then you can make develop some. So that's why we are going to do a classical simulation. So which shows you like which are proper point to stop. For instance, in the figure B, that if you know that you are away from this possible quantum speed up regime, and then because the rest of the regime you have to be you have to introduce lots of error, and then that you will know that after like 50 iterations, okay, you have to stop. So then you can like set make that experience and set that to be like 50 iterations. This has to be done in terms of like experiments. So we didn't have a way to like determine this kind of strategy in theory. So you have to keep trying.
Right. So for that one is like empirical experiment to kind of like get for a specific problem when to stop and when to restart to get the model into a dissipative regime to utilize the quantum algorithm that you propose.
Yes. Or if you already know the Hessian eigenvalue spectrum, you can try to have an estimate. There are formula in the paper that allow you to estimate balancing the error, and you can try to calculate it analytically. But you have to know the Hessian spectrum in order to do that. So that might be like a computationally not very easy. I'm not sure how to compute that quantumly in a large scale quantum computer. Even for classical computation, computing Hessian eigenvalue is hard. So part of the effort in this work was actually that we have the code to do Monte Carlo computation of large scale classical machine learning model Hessian eigenvalues. Because if you have n parameters, then your Hessian eigenvalue is n, right? So your matrix is n by n. Hessian matrix. And if you have 100 million parameters, it's going to be 100 million times 100 million. And then you have to diagonalize that matrix. That's going to be very, very hard. So what we do is some empirical partial empirical Monte Carlo simulation that allows you to compute part of the Hessian, and then we heuristically feed the part of the unknown part of Hessian in the middle. So that corresponds to another classical machine learning work that also have been published by my collaborator in the last year. So then this technique itself also contains lots of engineering effort in order to have a relatively accurate estimation of the Hessian eigenvalue in a large scale. So which is already like challenging and also are like a part of our like contribution.
Right. Thanks. Okay. One final questions. Like, I'm just curious about the time that you run about whole simulations and how long does it take you to kind of do the simulation to do the training, to calculate the Hessian and stuff like that. So do you have a kind of like classical computational time that that you're kind of aware on top of your head that you can use?
We write the experimental details in the paper, and
Oh,
actually
okay.
like
Is
each
it in
like
the appendix?
in the appendix.
Okay,
So
okay. I haven't like go through
actually, if you redo the whole experiment that for in that number of parameters, like I think 7 million parameters, we have to do it in total in a month. But I'm not sure if there is a record for the historical time added together, because we use Argonne National Lab with GPU in order to do the simulation, and they have to have lots of like time for waiting in the queue in order to use that resource. So for each, but in total, we do take this numerical calculation takes a half a year in from our resource in order to do that. But we are not also not have that much resource. If you have lots of high quality GPUs, then it's much easier. But we are using it in the national lab, but we don't have a very like high priority according to other people's work. So
Right.
comparing to other people's work, so we have to wait in the queue for a while. So in total, those calculations like takes half a year to finish all the tests. But we if you subtract the time waiting in the queue, and I don't know how much time actually is useful for computation.
Okay, yeah, sure. Okay, I think because of time, then we should like stop it now, stop the seminar now. And thanks again, like Junyi, for the very, very informative and interesting talks. And I believe like your work will kind of like be inspires people to look into another direction of quantum machine learning instead of just proposing some models and then just try on the data set, but instead think cleverly of like what quantum computer could be used in like even for classical machine learning speed up in like as what you shown in kind of statistical stochastic gradient descent. So I think we can like close the seminar now and yeah, see you guys. Thanks.
Thank you very much. Bye
Yeah,
bye.
bye.